Welcome to this explainer. Today we're jumping right into the Nepal National Building Code, specifically the rigorous NBC 10-5-2020 update, and we're going to translate it into a clear step-by-step ETABS workflow. If you've ever stared at a dense structural codebook and wondered how to actually apply those massive equations to a real 3D model, well, you are in exactly the right place. All right, let's take a quick look at our roadmap. We're covering model and material setup, calculating seismic loads, checking interstory deflection, column beam capacity checks, and finally, final reinforcement detailing.
You can really just think of this workflow as the life cycle of our structural analysis. We'll define the physical constraints, hit it with the earthquake loads, run the safety checks to see if the building breaks, and then export the blueprints.
Okay, kicking things off with Section 1, Model and Material Setup.
We're working with a pretty standard digital twin today. It's an ordinary 3-story residential building with a stair cover, a plinth area just under 92.95 square meters, and a 3.2-meter story height. Now, crucially, we are relying entirely on the reinforced concrete frame to resist all the stress. We're assuming zero structural contribution from the masonry infill walls. You know how it is. It's a conservative, incredibly safe engineering approach. But before we can even think about running this simulation, we have to translate these physical construction materials into exact mathematical weights. Reinforced concrete, that's our heavy hitter, coming in at 25 kilonewtons per cubic meter. But the dead loads add up super fast. You've got brick masonry at 19.2, marble for the staircases at 26.5, screed at 22, and plaster at 20.4. Getting these baselines right is absolutely essential. I mean, this is the massive static burden our frame carries before the ground even starts shaking. Buildings are unimaginably heavy, and the math just doesn't lie. Moving right along to Section 2, Calculating Seismic Loads. This is where things get really interesting, because the horizontal-based shear methodology has evolved drastically. Just look at the old 1992 code versus the 2020 update. We went from a simple basic coefficient formula to dividing a spectral shape factor by ductility, which, as we know, is basically how much the building can safely bend, and overstrength factors. It's a massive leap in analytical precision. And this graph right here is the absolute visual heartbeat of the new code. It's the spectral shape factor. It dictates our seismic baseline based on soil types, all the way from hard rock down to soft soil. See how, as the natural period of the building changes along the bottom axis, the design acceleration shifts vertically. We literally feed this curve into ETABS. It's like teaching the software exactly how the specific ground beneath us will amplify a quake. All right, let's dive into Section 3, Checking Interstory Deflection. Before we hit run on the simulation, what are the actual boundaries? Well, to prevent a collapse, or even just preserve everyday usability, the ratio of interstory deflection to the story height cannot exceed 0.025 at the ultimate limit state. That's our absolute maximum stress event. And for the serviceability limit state, designed to make sure the building remains functional without severe architectural damage, we're capped at 0.006. So check out these ETABS output charts. They show the predicted structural drift across all the stories. The red and blue lines represent movement along the global X and Y axes. You can really visualize the building bending and swaying from the base up through stories 1, 2, 3, and the stair cover. And obviously, the wider that curve gets, the more the floor shifts laterally relative to the floor right beneath it. Moment of truth. This is where we prove if the design actually works. When we apply the code's required ductility factor multiplier to the raw ETABS deflection in the X direction, boom, it sits exactly at our limit of 0.025, right on the money. And in the Y direction, it calculates out to 0.0244, which is safely below the threshold. That means our frame passes the ultimate structural check. The building is going to stand. Next up, Section 4, Column Beam Capacity Checks. So this introduces the column beam moment capacity ratio. You guys know this concept. It's a strict engineering requirement that ensures the sum of the column end moment capacities is strictly greater than 1.2 times the sum of the beam end moment capacities at every single frame junction. Defining this ratio is absolutely critical. Mathematically, it guarantees that classic strong column, weak beam behavior. In a catastrophic overload event, we want those beams to yield and fail long before our columns do. It prevents that total pancake-style building collapse, which is obviously every structural engineer's worst nightmare. Here is the actual text from Clause 4.4.4 of the Ductile Detailing Code. This is the exact mathematical inequality every single column and beam intersection in our model has to satisfy.
It's not a polite suggestion, right? It is a rigid, uncompromising legal code requirement for earthquake resistance. To put this into practice, we just tell ETABS to process the design using the specified IS 456 standards. It runs these immense calculations across every single joint in our 3-story frame. And for our model, spoiler alerts, every single component passed the ultimate capacity test. Our column-to-beam strength is exactly where it needs to be.
Finally, Section 5, Final Reinforcement Detailing.
This digital blueprint right here is our reward for all that math. This elevation view details the precise reinforcement area required for the columns to satisfy everything we just went over. The numbers displayed along the vertical lines tell us exactly how much steel rebar has to be packed into each specific column section to safely carry the heavy seismic and dead loads. Same story for the beams. ETABS generates this incredibly detailed map of the exact rebar needed. Looking down at the floor plan, you can easily see the precise reinforcement areas calculated for the top, bottom, and midspans of every single beam in the grid. It's a highly optimized, completely code-compliant map that is ready to be handed straight over to the construction crew.
As a quick final step, let's look at our structural efficiency. When we check the column rebar percentages for our 400 by 400 columns, the steel requirement drops from 1.42% down on that heavy bottom floor to a very clean 1.00% on the upper floors. We can use this kind of granular data to optimize construction material usage on site, while obviously staying mathematically sealed within the safety codes.
So there you have it. We've successfully bridged the gap between codebook theory and practical software reality. We established our materials, calculated severe seismic loads, verified that our interstory drifts wouldn't snap the frame, confirmed our columns were stronger than our beams, and generated the exact steel requirements. It's a brilliant, complete workflow. But the ultimate question remains for you. With NBC 105-2020 mastered in ETABS, is your next building ready to stand the test and weather the storm? Thank you for exploring this framework with me, and I really hope this explainer helps you build stronger, safer structures.